Hey guys, let's start with the very first topic for a data structure class, algorithm analysis. In this class, I will start introducing you the idea of the BigO notation so that you will understand how do we analyze a program. And then we will look into two examples. The first example is something you already understand, search problem. So in the array, you try to find a value. And how do you write a program to do so? The second question is going to be more interesting and challenging, which is called maximum continuous subsequence problem. So let's starting with the BigO analysis. For a program, we try to implement it, or we try to ask the computer to solve a problem. So the algorithm is the method of how we solve the problem. This method need to have the following properties. First of all, it must be definite and unambiguous. And then it has to be simple enough to carry out by computer. What does that mean? That means for a computer, you actually know that computer understands only two things, 0 and 1. Every single thing is based on that. So the algorithm is going to be some method that's simple enough to carry out by a computer, which means that the computer can only understand 0 and 1. And you try to write the programming language to make sure computer will execute your thinkings. And then, more importantly, it needs to be terminated after a finite number of operations, which means that it needs to go to the end. And probably more importantly, it needs to end in a reasonable amount of time. So the algorithm plus a data structure, so the method that you try to use, plus how do you store the data, the algorithm will access the data and then form the programs. So that is the connections between the algorithms and the data structure. In this class, we focus on data structure. After this one, you will take the next class, CSCI 3330 algorithm class, to combine all of those things together, and then you will be able to write some programs. So why do we need to do the algorithm analysis? As I mentioned, we need to make sure the program ends in a reasonable amount of time. That's why usually when we run a computer-based, because we need to process a large amount of data. If there's only 10 numbers and you want to find the average, you probably don't need to open up Visual Studio and then try to write a C++ program. You will just use a calculator and do so. Usually when we bring out the computers into practice, it's because there's a large amount of data. So when we run a program on a large amount of data, besides to make sure the program runs correctly, we must make sure that the program terminates in a reasonable amount of time. So that's what we want to do, the algorithm analysis, and we want to make sure it is efficient. So algorithm is a clearly specified finite set of instructions a computer follows to solve a problem. So it will go step by step and then try to follow your instructions and solve the problem. Algorithm analysis is a process to determine the amount of time, resource, etc. required when executing an algorithm. So the BigO notation is something that we use to do the analysis. What is BigO notation? A BigO notation is used to capture the most dominant term. So that is going to be the most important thing that we want to capture in terms of the growth rate. So again, BigO notation is used to capture the most dominant term in a function. So we don't care about the minor things. We only care about the most important thing. And to represent the growth rate, it's also called a sympathetic upper bound. For example, and this example tells you what is BigO notation. Saying that we have an equation or we do algorithm analysis, understanding that n representing the input data. So this algorithm will require 100 multiplied n cubed plus 30,000 multiply n. In this case, because n cubed is the most dominant term, and that is the one dominates the execution time, and therefore we will capture that by BigO of n cubed. In the other example, you can see that there's n cubed in the domination, n to the power of 5 and nn. We understand that the most dominant one is n to the power of 5, so that is the only thing we care about. Other things will contribute to some execution time. However, the most dominant one dominates everything, and that is something we care about. Let's look into some simpler examples. And the first example is something you already know. When we try to run finding the minimum element in an array, and this array is a regular array, it's not sorted, it's pretty straightforward. So in order to find the minimum value in an array, we need to use a loop to go through every single item and then find the minimum one. Whenever it finds a smaller one, it will replace. So when we walk in the beginning, we find -2 is the smaller one. We say the current minimum value is -2. We then move to 4. 4 is now smaller than -2, so we don't care about that. We go to the next one, understanding -3 is smaller than -2, so we will replace the current minimum is -3. We will walk through every single item. When we hit -4, the current minimum is -4. When we hit -8, we understand the current minimum is -8, and we walk through every single item, understanding that -8 is the smallest element. So take a look at this carefully. In this example, we have 10 elements. So the loop needs to walk through all 10 elements to find the answer. And therefore, this is the algorithm that requires n elements, BigO of n operation. So this is something that we call a linear operation. In this example, you need to understand, for saying that if we have 10 elements, and that requires 1 second for computer to complete. Now, if we expand 10 elements to 20, it will go proportion from 10 to 20 is 2 times to our input data size, so it will probably take about 2 seconds to finish it. That's the idea of the linear operation. Let's take a look at the second example. The second example is this one. On an XY plane, we have several points. Over here, there's about 10 points on the two-dimensional space. Saying that the problem is that we want to find the 2 points that are closest to each other. So basically, you can see that if there are 10 points, they have their distances, and if I'm asking you to find the 2 closest points, you can probably quickly finding out that these 2 are the two closest points. However, for a computer to do so, you cannot just put this figure into a camera and then tell the computer, say, hey, look, what are the 2 closest points? What a computer would do, or when you as a computer scientist need to solve this problem, you will need to write a program and then calculate what we call a distance matrix. To find the 2 closest points, we need to use the nested loop. So we have one loop go through all the items from 0 to 9 points, and then you need to have another loop that are nested to that one to form a distance matrix, which means that you need to calculate all distances among all the points. So think about this. Since we have 10 points, the distance matrix would be a 10 by 10 matrix. That means you have 100 points, 100 distances that you need to do the calculation. So, in this case, if we have n points, we need to calculate n square values. In other words, if I have 100 points on a two-dimensional space, how many distances that you need to calculate? It's basically 100 to the power of 2, which means it's 10,000 points. This is the idea of an n square operation. Of course, if you are good in math, you will understand one thing. we don't actually need to calculate the whole distance matrix. First of all, the diagonal value are all 0 because the distance from point 1 to point 1 is 0, point 2 to point 2 is 0, point 3 to point 3 is 0, so we don't really need to do the calculations. On top of that, this is a symmetric matrix. So the distances over here is symmetric to the distances over there, and therefore we only need to calculate half of that. That's totally correct. In fact, in reality, instead of 100 points for a 10 points example, we only need to calculate 10 multiplied 10 minus 1 because the diagonal value are all 0, and then only half of that need to be calculated. So this is actually how many distances that we need to do the calculation. However, remember when we are looking into the BigO analysis, this value is equals to half of n squared minus half of n, and after the BigO notation, n squared again is something that we care about. Therefore, this is what we are talking about, the BigO analysis. At a certain point, as a computer scientist, I'm more interested in this compared with the mathematicians. The third example is try to find the collinear points. So you try to see if there is 3 points are on the same line. Therefore, to do this, you actually need to find out all combination of 2 points and find the line of that and then test on all points again. So this will take you to the n cube of operation. Of course, this is going to require a lot of operation time. Okay. So summary of this one with these 3 different examples, each one of that, in order to solve the problem, they have their own BigO notations of the execution time. So take a look of this math operation. If n equal to simply 1,000, and 1,000 to computer world is a pretty small data set, there's actually a lot of values that need to do the calculation, of which this value comes from the n cube operation. So we only again care about the most dominant term. There are several BigO notations that existing in computer science world. There's something called BigO of 1, that's constant time. BigO of log n, log time, BigO of n linear, n log n, n squared, n to the power of k, which is what we call a polynomial time. If we try to map that into a 2-dimensional space, you can see this one. And you need to understand the y-axis is actually 2 to the power of 2. So you can see that this is the growth rate of each operations. BigO of 1 is something very interesting. Say, what is a constant time? That means no matter how big your data set is, that doesn't change the execution time of it. The best example is actually in a sorted array, and you try to find the minimum or maximum. So you know, as a sorted array, the minimum or maximum will stay on 2 ends. So no matter how big it is, you know where to look for. And that's the idea of the BigO of 1. And you see the growth rate n squared is actually a pretty expensive already. When it goes to 2 to the power of n, or n factorial, or n to the power of n, those are something that problems of the those are the problems that computer cannot solve. So, as the summary of this topic, I want you guys to have some practice. So there are 5 examples of the operations. I want you to hit the pause and then try to find out what is the BigO notations of each operation. So please do that. Assume you come back with all the answers. You need to see that for the first 3 operations, they are pretty straightforward. For this one, n to the power of 2, when you multiply into that one, you will actually end up with n to the power of 2 plus 3. So you need to understand, when you multiply things in, you will get n to the power of 5. This one is something very interesting. This is saying that this program requires 2 parameters to do the operation. So both of them need to be